All right, hello everybody. We had this problem that we did the other day that threw a lot of you for a loop. It's about a lighthouse, and so I wanted to discuss how we can find the rate of change of the beam of light on the lighthouse as it moves along the shoreline. And the reason I have Desmos pulled up is just to show you how the graph of the rate of change varies depending on the angle and why that makes sense in the context of the problem. So first I'm going to draw you a beautiful picture of a lighthouse. It helps if you turn your pen on. Okay, here's your lighthouse, and then you have suspiciously a straight shoreline over there. And what happens is the lighthouse's light shines out and the lighthouse spins. So at different times, your beam of light is shining at different points along the shoreline. Shines here, shines down here, shines down here, and then eventually the beam of light shines parallel to the shoreline. It doesn't hit it at all. And then for half of its rotation, it's just shining out to sea. And then it loops back around over here and starts hitting the shoreline like this. So at every angle, the beam of light is hitting the shoreline at a certain point. And what you'll notice is as that lighthouse rotates, the point that it hits the shoreline at, let's call that point X. The way that I've drawn my rotation, the point X moves down the shoreline like that. And the question is, what is the relationship between how fast the angle on the lighthouse is spinning and how fast the point on the shoreline is moving? Again, at a certain point, the light will no longer hit the shoreline, so the point X disappears for about half of the rotation when the light is not hitting the shoreline. But for the other half of the rotation, the light is hitting the shoreline very high up and then shining down along it, and the X value goes down the shoreline with the way I drew the picture. Okay, we're also told that the lighthouse is 100 meters away from the shoreline. And so no matter where I draw that point X, we create a right triangle. We could consider that right triangle, or we could consider this right triangle, or we could consider this right triangle here. And each of those right triangles has a certain angle right there. X is the opposite side to that angle, and 100 is the adjacent side. So if I set up my trig ratio, I know that tangent of the angle is equal to X divided by 100. And that's true if X is up here. It's also true if X is down there. It's just my picture looks like this with a theta below the perpendicular line. If I'm trying to find a rate of change with respect to time, I'm going to take d over dt of both sides. I'm going to take the derivative with respect to time of the whole equation. The derivative of tangent is secant squared. But I'm not thinking of theta as just an independent variable. Theta is changing over time. So I'm taking the derivative with respect to t, so I use the chain rule. I multiply by d theta over dt. Then I get to x. Again, x is not just an independent variable. It's some function. It's sliding down that shoreline. I don't know exactly what that function is, but I do know that if I take its derivative with respect to time, I get dx dt. Because 100 is just a constant, it just sits right there. Now the question tells us also how quickly the lighthouse is spinning, and it asks us to figure out how quickly the beam of light is moving. So we're asked to solve for dx dt in terms of the other pieces. So I'm going to go ahead and multiply by 100 to get dx dt by itself. So then we have 100 secant squared of theta d theta dt. So we need to know either one of those. We need to know either theta or d theta dt to finish the problem here. They told us that the lighthouse rotates 6 times per minute. Okay, so the lighthouse does 6 full rotations in 1 minute. So 6 spins per minute means think about the angle of a full spin. I'm going to use radians here. 6 times 2 pi per 1 minute. So that's 12 pi over 1. And you can look at your units here, d theta dt. The units match up. Theta is 12 pi. That's how many thetas it does in 1 minute. That's dt. So then I know that at the particular moment that I care about, all I need to plug in is theta. So there's 2 different moments that we can analyze. Oh, well, there's an infinite number of moments we could analyze. But one moment that we might care about is when the x value is right here, directly across from the lighthouse at a right angle, so that the beam of light is hitting at a right angle. And so there is no triangle right there. Theta is equal to 0. So I'll do that up here in the top right corner of the screen. When theta equals 0, our derivative, 100 secant squared of 0 times d theta dt, which is 12 pi, that's going to be my speed dx dt. And so if I do that, secant squared of 0 is 1, so I have 100 times 12 pi, so I have 1200 pi, and that's dx dt. So at the moment when the lighthouse is directly across from the shoreline, when the beam is shining at a right angle to the shoreline, the beam is moving 1200 pi. That's the speed. Now let's think about our units here. I know that 100 was measured in terms of meters, so I'll stick a meters unit on there. 100 meters. I know that secant squared does not have any units on it because secant is a ratio of sides of a triangle. If you think about secant, secant is the reciprocal of cosine. Cosine is adjacent divided by hypotenuse. So cosine is already unitless because it's meters divided by meters. Secant is also unitless. Now, 1200 or 12 pi over here, I wrote it in terms of theta per second. And so you get this point right here, and this was really confusing to me, was that this feels like it should say meters times theta per second. Sorry, I shouldn't say theta. I should say radians, because that's the measurement of theta. So I'll write rad in there instead. And this is probably my favorite part of teaching math, is when I realize that I don't know something, that I was confused about something. I was confused. Why do I have radians per second? Meters times radians per second feels wrong. Well, it turns out that a radian, just like how secant doesn't have a unit on it, a radian also is a ratio of 2 lengths. A radian is a ratio of the arc length to the radius. And so just like how I said secant was meters divided by meters, the units canceled out, radians are also meters divided by meters. So we can also cancel out the rad and we get meters per second. And that's why I used radians, because had you used degrees, degrees are not unitless. So that you would have to think about how to convert back from degrees per second, because you'd have meters times degrees per second, to this value here. Okay, so that's when theta equals 0, 1200 pi. If we made theta equal some other value, say theta was 50, so the beam is now 50 meters down from that point, then we have 100 secant squared. Oh, I'm sorry, not when theta is 50, when x is 50, when we're 50 meters down, not 50 radians. That'd be a crazy big radian. When x is 50, then we'd need to figure out what theta is. Okay, so if we made x 50, let's go back to our triangle. We have 100 here and 50 here. Okay, And so then the secant, we need to figure out what angle that has. You could use the arctan of a half because the opposite over adjacent is 1/2. That's not going to come out to be a really nice number, but times 12 pi. Grab a calculator and it'll give you some sort of estimate here, approximation of it. So 100 times secant, so I'm going to go 1 over cosine of the arctan of a half. Make sure I close all those parentheses. And then it's secant squared, so I'm going to square that and multiply that by 12 pi. So here's what that looks like in the calculator there. And so then I get 4712.39. The other one of 1200 pi was 3700. So you can see it's getting faster. If we increase the speed more, it'll get faster and faster. Okay, so let me show you this as a function. So let's type it in. We have that our dx dt is 100 secant squared of x times 12 pi. All right. Where is that graph? Huh, interesting. Oh, because it's so big. There it is. Okay. So let's adjust our values here. Let's make our x values. I'm going to clear the screen out so I can't see what I'm doing. I'm going to get the x values to go for just like one rotation. So let's say 0 to 2 pi. And then the y values are fine. So you can see here that when x is 0, 1200 pi is the lowest speed. And then as the light beam goes down along the shoreline, it speeds up and speeds up until it gets infinitely fast. And then it picks up again on the other side of the rotation. Okay, so there you go. Please let me know if you have any questions. And thanks for watching.